Hello again. This is Math 1428 Remote Delivery for April 15th, 2020. And we are covering section 5.5 in your textbook, and I encourage you to perfect your understanding by using buttons like this as you watch this video. The base exponent property tells us that if the base is the same, a to the x is equal to a to the y, it's a in both cases, then x equal y. Certainly if x equal y, then a to the x equals a to the y. So you see this really goes both ways. This is if and only if. This will help us solve some equations. Similarly, the inverse, the logarithm, is also 1 to 1. That means if the log base a of m equals the log base a of n, the only way that can happen is for m to equal n. Let's look at some examples. So here we have 2 to the 3x minus 7 equal 32. The algebraic solution is to realize that 32 is 2 to the 5. So you see I have 2 to the something equals 2 to the something else. So I know from the property we just discussed that the exponents have to be equal. 3x minus 7 equal 5, and that tells me that x is equal to 4. Now, if we wanted to use the intersection method using our calculator, we would graph the left-hand side of the equation, and then separately we would graph the right-hand side of the equation, and we'd use the intersect function to find out where they intersect. And again, we would find the solution is 4. You're given an opportunity to perfect your understanding by doing this exercise 7. Let's look at another example. Here we have the problem 3 to the x is equal to 20. Now it turns out 20 cannot be written as a perfect power of 3, as an integer power of 3. So that means we have to do it differently. The algebraic solution is we're going to realize that, oh, I can take the logarithm base 10 of both sides. Then I use the property of logarithms that tells me that this x comes out in front. So as x times the log 3 is equal to the log of 20. I just took logarithms of both sides. Now this is a constant, so this is like 5 times x, so I'll divide both sides by what would have been the 5, but in this case it's the number that is the logarithm base 10 of 3, so x is equal to this exactly. This is an exact answer. If you plug this into your calculator, you get an approximate answer like this. Again, we can use the intersect method. We can take y1 to be the graph of the left-hand side, y2 to be graph of the right-hand side. Use the intersect function, and we conclude that the solution is approximately this. Again, we get approximate solutions from the graphing calculator often. You're encouraged to perfect your understanding by giving Exercise 11 a try. Now in that example, we took the common logarithm on both sides, but any base would give you the same answer. For example, if we solved, if we took the base log 3, we would have got this expression, and then we could use the change of base formula and get this as an answer. Or there is a function that you can do this using many of your calculators. The TI-84, our standard platform, use a log base operation that is discussed here, and that will give you the answer directly without using the change of base formula. Let's look at a more complicated problem. Here we have e being the base, so we have 100 e to the 0.08 t equal 2500. We have an algebra solution and a graphical solution. The graphical solution would be to graph the left-hand side of the equation and graph the right-hand side of the equation separately and determine the point of intersection as we've discussed before. And the point of intersection is approximately 40.2. The algebraic solution is if we take the natural logarithm of both, I guess the first step I would do is I would divide both sides by 100. So I would have e to the 0.08 t equals 25. Then I would take the natural logarithm of both sides. Now the natural logarithm of e to some power is just that power because they're inverse functions, so I would have this, and t would be dividing both sides by 0.08. I get this. Now this is the exact answer to the equation, but if you plug it in a calculator, you'll get approximately 40.2, and it matches. Again, you're invited to perfect your understanding by working on problem 19. A different example is in example 4. We have 4 to the x plus 3 is equal to 3 to the minus x. Again, the graphical solution is we would graph the left-hand side of the equation, and we would graph the right-hand side of the equation, and we'd see where do they intersect. And if we use that technique, we would find they intersected approximately minus 1.6737. The algebraic solution is I would take the logarithm, let's just say base 10 of both sides. Then I would use the fact I would get the exponents out in front. So this x plus 3 comes out in front of the log base 4, and the minus x comes out into the log base 3. Now I will distribute because this is just a number. So I take x times log 4 plus 3 times log 4 again. And now I collect terms that have the x's on it. So I'm going to add this term to both sides, and I'm going to subtract this term from both sides. Then I can factor out the x. And this, even though it looks like a complicated expression, it really is just a number. So I can divide both sides of that, and I get x is equal to this. This isn't an exact answer, but it's approximately, if you plug this into your calculator, minus 1.6737. Again, you're invited to perfect your understanding by doing problem number 21. Here's problem number 5. We have e to the x plus e to the minus x minus 6 is equal to 0. Well, the graphical solution, we could use the 0 method and try to find the 0 of that function. We've learned how to do this. We find that x is approximately, and there are two solutions. There's one over here and there's one over here. You have to get both of them and use the feature 2 times, but the solutions are going to be approximately minus 1.76 and 1.76. The algebra is a little more complicated. What we're going to do is we're going to realize that this e to the minus x is 1 over e to the x. And then we're going to get a common denominator. The common denominator is going to be e to the x. So I multiply top and bottom here by e to the x to get e to the 2x. I multiply top and bottom by e to the x here, and I get, or I'm multiplying all the way through by e to the x, I guess what I'm saying. And then here I multiply by e to the x, and I get minus 6e to the x. Now, this is quadratic in form because I have something squared minus that something, 6 times that something, plus 1. So you see, if I let u equal e to the x, I can have this quadratic, and I can use the quadratic formula to find out what u is. But then u is, I have to say that u was e to the x, so e to the x is equal to either of these numbers. I take the natural logarithms of both sides, and I get this expression. And that's an exact answer. If I plug it into a calculator, I will get this and this. Again, you're invited to perfect your understanding by looking at exercise 25. Here we're solving logarithmic equations now. We're going to solve logarithm base 3 of x equal 2. Well, the algebraic solution actually is quite simple here because we just use the definition of a logarithm, changing the logarithm expression to an exponential expression, and we get x is 1/9. The graphical solution is we can use the change of base formula and look at this curve, which is going to be the left-hand side of the equation, and this being the right-hand side of the equation, and see where they intersect. And again, you get it is 1/9. Now, when you do this the first time, you get 0.111 repeating, but you can change that to a fraction using the fraction function. that is found in the math and number menu, and here you can change things to fractions or decimals. Again, you're invited to perfect your understanding by doing exercise 33. Here's another logarithmic equation that we're trying to solve. Log of x plus the log of x plus 3 is equal to 1. And so what we would do is, if we're doing the graphical solution, we would graph the left-hand side, we would graph the right-hand side and use the intersection method that we've studied before, and we see the solution is 2. The algebra solution will allow us to use properties of logarithms. Here we get this is the sum of the logarithms, and we know that that is the logarithm of the product is equal to 1. And then I use the exponential form of this, so 10 to the 1 is equal to this product, and I end up with a quadratic that I have to solve. Now this quadratic factors, and I get x minus 2 and x plus 5, and so I can check to see what my solutions are. Now I have to check these solutions because they have to fall in the domain of the original problem. But if I check, I find that 2 will work, but minus 5 will not, so I reject this answer, and the only answer that we have is 2. Problem 8. Again, this time it's a similar problem. It's logarithm base 3, but we're subtracting this time. So from algebra, we will find that the difference of the logarithms is the logarithm of the quotient. Again, I'm going to use the exponential form. So 3 squared is going to be equal to this expression. That's going to be 9. I solve this by multiplying both sides by x minus 4. And I find that x is equal to 5 when I solve that. And it does check, so the solution is 5. The graphical method is I changed this one to be the left-hand side is this. I'm using the change of base formula to write these, and the right-hand side is simply 2. And I will solve the intersection of these two, and I will get that the solution is 5. Again, you're invited to perfect your understanding by doing problem 45. Example 9. We're having the natural logarithm of this expression minus the natural logarithm of this expression is natural logarithm of x. So what we have here is this is the logarithm of a quotient. And then I can just raise both sides to the, I can use this as an exponent, this is the exponent, and or use the one-to-one property. Let's just talk about the one-to-one property. So since the ln of something is equal to the ln of something else, the something equals the something else. I can solve this by multiplying all the way through by x plus 5. I get a quadratic, and the quadratic factors. And now what I'm going to do is check to see if these are solutions. X equal 2 does check and is a solution. X equal minus 3 does not check because you have to take, that would be a logarithm of a negative number. And so that tells me that the only answer is x equal 2. And that's the same thing that we find on this side. We graph the, in fact, we move this over to this side this time, just use the 0 function. That makes this side equal to 0. And we can find the 0 of this, and then it is 2. There's only one solution. Example 10, we're solving this one. And it turns out that this would be a very difficult problem to try to solve. It is highly nonlinear. So the only solution we have is the graphical solution. So we're going to take the left-hand side, here's the left-hand side, as one function, and we're going to take the right-hand side as the other function. We'll use the intersect method. You should get this, and so you get two approximate solutions. It intersects here and here, so you have to use that intersect method twice. So make sure that you know how to do that. And you get the solutions are negative 6.471 and 6.610. And again, you're invited to perfect your understanding by trying exercise 67. So now, more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, please take care of yourself and of each other. See you in class.